Good afternoon and welcome to this afternoon's JPBM Communications Award Lecture. I'm Michael Pearson with the Mathematical Association of America. We're part of JPBM. I'm really delighted to be able to recognize Grant Sanderson today with one of this year's Communications Awards. Grant is the creator and founder of 3 Blue, 1 Brown, which is an effort to provide visualization of mathematics, and it's a YouTube channel, easily found. I hope you'll take a look at it. I had done my homework, as I'm supposed to do when I was warned to do this, and written out a nice introduction, which of course I can now not find on my electronic device, which is supposed to give me that. But I'll say, I went on the site, and as a harmonic analyst, I've spent a good bit of time thinking about convolutions, convolution kernels, and so forth. And I was really immediately attracted to see what Grant would do with convolution. He has a nice video presentation. What's the introduction to convolution? And some of you may know that the German word for convolution is Faltung, folding. And I think the video that Grant does with that really sort of makes that dynamic and shows you why folding is such a great word for convolution. So I encourage you to look at that one and any others that catch your eye. In any case, Grant graduated from Stanford University from Math and Computer Science in 2015. He spent some time working on videos and instructional materials for the Khan Academy, and then but now he's turned his full-time attention to 3 Blue, 1 Brown, and there's some really great stuff there, and without further ado, I'll let him tell us about it. Thank you. Thanks, Grant.
Thank you very much for that very warm introduction. I want to start just by saying a very heartfelt thanks to the members of the Joint Policy Board for the award. I will admit it is a little bit intimidating to receive an award for communication and then to be asked to immediately communicate to a room full of people I have high respect for. I'll do my best, but I couldn't help but notice that a lot of the names on the list for this particular award in past years were just personal heroes of mine who served to inspire me a lot in getting started. Names like Steve Strogatz or James Glick or Matt Parker all come to mind, but those are just a few of very, very many, so I want to say thanks there. Broadly speaking, I want to talk about math communication itself and some of my thoughts around math communication. But this breaks into a number of different categories, and it's kind of a hard thing to think about as a unified whole, because one component of that is education, and even that, it feels wrong to loop into a single group because, education before university in math and education undergrad and on have a very qualitatively different flavor to them and how you might think about what approaches are best or what's the typical engagement a student has. And even that is very different from other forms of communication that happen, presenting one's research, or popularization, which is probably the bucket that I fit most closely into, if I had to choose just one that's where I actually sit. But I do think it's very helpful, whichever one of these slices you find yourself in, to think about them as intersecting each other and a lot of the value coming from that intersection. Some directions here are obvious, like if you're in education, it doesn't hurt to think about it as a popularization effort. If you want to popularize something, you try to make it more engaging. You try to connect to things that people are already interested in. It doesn't hurt to do the same if it's in a classroom. But I also think on the flip side, as someone who popularizes things, or at least tries to, it's often not the right approach to do that head on and think, how can I make something that's going to reach the most people, has the most clickbaity title and the like. But what I've noticed is people just want to learn. The thing that makes something more popular, or the thing that gets more reach, is often if I do something that's meant more as a classroom supplement. Because people don't want to feel like they're just being watered down or talked down to, instead having a sense that what they're staring at is the authentic material, as if they were studying it and becoming an expert in it. I think that's a very inspiring feeling. So I titled this, Raising the Ceiling and Lowering the Floor of Math Exposition, referencing the fact that I think some of the efforts that we can make in trying to popularize it to reach more people can also make it more interesting to those who are already experts in it. But if I wanted to be a little bit more provocative in how I went about this talk, I could just as easily give what I have in mind the name of Math's Pedagogical Curse. Because I really do think there's something strange going on with math in particular in contrast to some other fields if we think about the perception that it has in the broader public. I think everybody in this room has probably had the experience, you're chatting with someone, cocktail party type environment, you mention you do something related to math, and the person says, as if there's no social taboo in saying it at all, which I guess there's not, oh, I'm not really a math person. Which is fair, you know, not everybody necessarily loves the subject that we do, but it's a funny phrase because, you know, you don't say that with respect to other things. But there's another turn of phrase that I've heard multiple different times that in some senses even more worrying than that one, which is the, I thought I liked math until. I have a very vivid memory, actually, of being a high school student touring different universities. And I was one of those students who always knew that I wanted to study math. I'd already fallen in love with it. So if I'd meet some students at the university, they asked their natural questions, oh, what do you think you might want to major in? I was like, I know, I want to major in math. And I remember this one student saying, oh, yeah, I thought I liked math. I even wanted to be a math major. And then I took a set theory class, and I discovered that I don't really like math, which is very sad. And I've heard variants of this through the years in various different contexts. Oh, I thought I liked math, and then I took a linear algebra class, right? I thought I liked math until, and then there's some point in which someone became disillusioned with it for whatever reason. Now that one feels like it's especially worth addressing because it's very hard, I think, to ignite the light of interest in the first place. And even if maybe the more important one to address is the broad scope of people who don't self-identify as math people, we could just as easily ask, what are we doing wrong such that we get some people that thought they liked math until? You know, maybe the answer is math is just harder than other fields. You know, it's just something you gotta roll up your sleeves and you know, work hard in order to attain, and not all people are willing to do that. I don't think that would be fair, though, because that kind of pushes the bump under the rug, where you have to instead ask, does it have to be that hard? You know, is there anything that we're doing that makes it harder than it needs to be? And I have a little theory for at least one component of what might be going on with math in what makes it distinct from other fields. And it has to do, bear with me here, with the legend of King Midas. So for those of you who don't know, in Greek mythology, or it's one of those kind of intertwined with fake Greek history that Aristotle and the like would tell to people, you have this king, supposedly, who lived around the 2nd millennium BC, named Midas. And you know, he does some good deeds that catch the attention of certain gods, and the god Dionysus says, I'm willing to give you a gift, name your gift, and I will give it to you. And Midas says, oh, well, what gift should I want? I think it would be great if anything that I touched could turn to gold. And Dionysus says, it is done. And Midas touches a twig, and it turns into gold. He's delighted. He goes back to his estate, and he starts touching all of the roses in his garden, and they turn into a beautiful metallic sheening gold. And he's just dreaming of all the wealth that he's going to have and the wealth that his entire regime is going to have. And then when he gets to the banquet for dinner that night, he touches the chicken leg sitting in front of him, and it turns to gold, and it's completely inedible. Or in other tellings of the story, the moment that he realizes something might be a little bit wrong with this gift is when his daughter comes up to him, and he touches her, and she completely turns into gold, and he doesn't have her anymore. And, of course, it proceeds where it's a story of redemption and the like. But the gift that is analogous to this, that I think math has, and it really is a gift, is a very special kind of exactness, where we have the pleasure of knowing with 100% certainty if a conclusion follows from the premises. Maybe not 100%, it's subject to our ability to fall for certain logical fallacies or to miss holes in an argument. But with as much precision as you could possibly hope for, math has this kind of exactness. And a lot of other fields would just dream of anything like this. Hard sciences get kind of close if we think of physics or computer science. But even then, they're subject to a little bit of controversy with different ways you might interpret something, or even the best experiments aren't 100% precise. The softer sciences get even further away from this. Most forms of writing and discourse out there are more unabashedly subjective. You might think of art criticism. It's not unworthy, but it lacks this exactness. And the gift that comes from this exactness is that it helps you move forward a field. You don't fall into the same disputes that you might otherwise when there's room for ambiguity and misinterpretations. And I think what it might even mean for something to be mathematical is that it has this level of exactness. There's a friend of mine who's a biologist, and anytime we talk, she always bemoans the fact that biology needs to become more of a mathematical science. Just how far could humanity progress if we could turn biology into a mathematical science? And presumably what she means by that is that you get a situation where you can draw conclusions from your premises with the same airtight, rock-solid rigor that a field like physics might have. The other really nice thing that this gets us, I think, is when you're writing something, like you're writing a textbook or a paper or a video or you're preparing a lecture, it gives a test for completion that no one else gets to have. We can have this clear notion of it's not done yet, and then at some point there's a sense in which it's done, where you can go through and you can make sure all of the definitions are completely unambiguous. We get to have unambiguous definitions. Everyone else doesn't get to have those. You can ask whether every object in the theorems that you reference have been previously defined. It's like a compiler checking code. You get to go through, and the answer is either clearly delineated yes or clearly delineated no. And then most importantly, for every claim that you make, you can ask, was it completely justified? And then that constitutes a notion of explanation in some sense. It gives you a clear point where before you got to that point, the paper wasn't finished or the lecture wasn't finished, but after that point, you can put a little bow around it and say it was finished. And like I said, I really do think it's a gift because it helps us move forward in a way that other fields can't. But there's a catch to this gift, where in the same way that the things that King Midas might touch and turn to gold, but this had a problem where he wouldn't be able to eat his food, the mathematician can touch anything, give it this notion of completely unambiguous rigor, but sometimes it runs the risk of leaving it, how shall we put it, slightly unpalatable to the average casual reader, or maybe a little bit harder to consume than it needs to be for a typical student. And I do want to emphasize, I don't think that it's a necessary thing that follows. I don't want to come across as implying that if something is rigorous, that means that it's not clear. It's a little bit of an exaggeration to make the comparison with Midas quite like this. But what I do think is possibly the case is that this allure of such a notion of exactness, where we can actually say that it is done in a certain sense, means that rigor serves kind of as a distraction, right? I have to tell you, there will be no year that I grow tired of this meme. I know it's a little bit old, but the staying power with this is just unparalleled. No, but I think it's the case that a lot of really good authors manage to achieve both rigor and clarity. And in fact, the point of rigor is often to add more clarity. But the thing that I suspect might happen every now and then is that because the rigor gives you this very clean, nice thing to think about, and because thinking about pedagogical clarity is a lot messier, it's harder to define, you can't put a bow around it, there's not one point when you've gone from not done to completely done, that after scratching the itch of knowing that something's been written completely rigorously, it's easy to call a work done when maybe we shouldn't call it done yet. And there's contexts where this is maybe okay, research papers come to mind, but in things that are more explicitly pedagogical, textbooks come to mind, I would propose that maybe it makes sense to invite into the culture a similar focus that we already have on the rigor of it, but instead onto something for the pedagogical clarity. And I'll give an example here, which is essentially just from the book that was sitting on my desk while I was putting together these slides. I actually love the textbook. It's really great. And one of the only reasons I feel comfortable highlighting it and poking a little bit of fun at one of the sections is because it otherwise holds up very well, and it's one I would unabashedly recommend. But I was thinking, okay, how well does the author tend to think about points of pedagogical clarity in addition to points of rigorous clarity? And one particular section that I was looking at was about something called the Poisson summation formula. Many of you might be familiar with it. It essentially says for a function which is sufficiently nice, if you add up the value of that function across all of the integers, it gets the same thing as if you add up the Fourier transform of that function across all the integers. It's kind of a wild formula, very useful in many different contexts. And the proof that the book gives is actually really beautiful. I liked it a lot. It starts off by describing a certain function a little bit out of the blue, but if you look at it, you notice that it has poles at all of the integers, and the residue at those poles are exactly the values that you might want to sum on the left-hand side of your formula. And essentially what the book does is it kind of, after handing down this construct, and after describing a certain contour that you might integrate along, and the context here was, it's in a setting of assuming people are familiar with the complex analysis up to the point in the book and know about contour integrals and the like. It goes through and shows how you can have a very elegant derivation of the formula basically by unpacking what this integral is saying, and step by step, it eventually turns it into the sum on the right-hand side. So it's very beautiful. It involves a lot of clever ideas. Things fit together nicely at the end. You can look back on it and I think as a writer, think, what more could you possibly want? It's as clean a proof as I could imagine. And I think there's a culture in math textbooks that sort of says once something is proven, that means it is complete. But if you try to add a secondary checklist that says, what are the pedagogical considerations, even though I think this is a great book, and even though I think the proof has a lot of staying power, there are dozens of other questions that I could think one might want to lead up to this particular fact with, or follow it with. To start off with, you could just say, what is this formula? How do you think about it? Why should you expect that something like this would be true? What are the circumstances that you might run into in the mathematical wild where you would think that this is something that you need to bring to bear? For example, it doesn't hurt to illustrate just a little bit, like, how do we parse what each side is saying? The left-hand side, which is adding up the value of the function for all of the positive integers, you could kind of think of as a extremely coarse Riemann sum for the whole function. And one of the terms on the right-hand side, if you take the Fourier transform just at 0, those of you who are comfortable with the matter know that that's just the same thing as integrating the function. And so what that tells you is that much of the left-hand side is already encapsulated just with the 0th term on the right-hand side. And the student might then be invited to think about how all of the other Fourier coefficients give you a sort of correction factor between the difference of this coarse Riemann sum and the area. And that instills a little bit of intuition around if you have an especially smooth function, one that stays very flat, that would suggest that less correction is needed in comparison to if it has high variation. When it comes to the proof itself, while the author gave a delightful proof, there were many steps where, like I said, it felt like it was handed down from on high. And what I would love to see, or would love to feel, is a sense of how I might have discovered that myself. I think it's hard to understate just how delightful it can be if you, as the reader, feel like the thing that was coming in is something that you kind of anticipated, and that it's validating, rather than feeling like you're the one who has to kind of validate that the monument that you're handed does the thing that's being claimed. And in this case, I think there's a longer description, but length isn't necessarily the enemy, that could provide a sort of path of rediscovery for the very elegant proof that potentially could give it even more staying power. Now, what I mainly want to ask through the remainder of this talk is, in light of the fact that we have such a satisfying checklist for rigor that really distinguishes math, and which I think draws the attention of the mathematician and the writer so alluringly because of how satisfying it is to go through that checklist and know that something's complete, is it possible to have something that's analogous for those of us who want to popularize or educate or otherwise communicate as clearly as is possible? Is there something that has the same sort of itch-scratching satisfaction of unambiguously knowing that you're there or you're not? It's not a fuzzy realm where someone just qualitatively says this writing vaguely seems better, but is there an actual set of things that we could assign a binary value to? And the reason I think that might be valuable is that, mathematician instinct is one that sort of likes this notion of definiteness. And so if we can put something a little bit more definite wrapped around the indefinite realm of pedagogy, that might be helpful. So you could probably brainstorm a lot of things that might come to mind if you're doing this. A couple that I happen to write down here is, does each definition that is written down have a motivating example? A reason you would want to define something like that, rather than seeing the examples come after the proof, after the theorem, and the like. Do the proofs feel rediscoverable? Like I said, it can be incredibly satisfying if a student feels like they knew what was coming. And whenever I put together videos, I really try to focus on a path of rediscovery, which makes it longer, but again, I don't think length is necessarily the enemy, as long as you're not being verbose about it. Another very simple consideration, maybe a little bit vague, a little bit hard to assign that binary check to, is, does it feel personal? Does it feel like an actual person is talking to you with a little bit of emotion and personality? I think that matters when it comes to how engaged someone is with something. And when you're more engaged, you remember things better. Another simple one, just are there diagrams? If something should be illustrated, is it illustrated? This is one that's very near and dear to my heart, as I'll get to in a moment. But there's all sorts of other things you might do. And I would actually be curious what anyone else in the audience thinks could be added to this checklist. What I wanted to do for the remainder is talk through a couple points that I try to think about as I'm putting together a piece of exposition or putting together a video. It's not a complete checklist. I don't think there exists such a thing as a checklist for pedagogy in quite the same way that there's a checklist for rigor. But I do think if we tried to invite that into the culture of math exposition, the attempt to write down such a checklist could go a long way. So the channel that I run, it's, for those of you unfamiliar, it's called 3 Blue 1 Brown. And in a nutshell, the premise is to give lessons that are as visualized as I possibly can make them. Not in a way that's superfluous, not in a way that has like flashiness for the sake of production quality flashiness, but instead, for a given topic, just make sure that each statement that's made, if it makes sense to, has some kind of diagram that went along with it, or some kind of animation. Now, part of this is because just as a hobby, one of the things I delight in is programming math animations. So this was sort of a love child between two different interests of mine, which is teaching math and then programming animations. But just to give a little bit of an illustration of what I have in mind, and then to also try to argue why sometimes making visuals like this isn't just a chore for the sake of adding more pizzazz to a lesson, but it can make it more interesting for the person putting together the lesson. I wanted to look at a video where the reason I made it was because of the visualizations I was playing around with. It wasn't that I wrote a script and then I started putting some kind of cartoon to the script. It's instead that I was playing around with trying to visualize something, and then by seeing it in a certain way, it gave me the framing for how I wanted to describe it to others. So the topic was the Riemann zeta function, and in particular, analytic continuation. And I opened the video with the usual motivations you might give for the Riemann zeta function, the status that the Riemann hypothesis has, that it contains information relevant to the primes, all of that. But the meat was to simply answer the question for a casual viewer who's kind of interested in math but don't necessarily want to assume they know too much already. What is it? What is this function? Which is, of course, a surprisingly intricate question to answer. And half of the answer is not that hard, which is to look at a certain sum that defines it, where you take zeta of s defined to be 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, on and on. So for example, an especially fun value to plug in here is something like 2, where you're adding up 1 plus 1/4 plus 1/9 plus 1/16, on and on and on. The sum actually converges. It was, for one period in history, a problem that nobody in Europe could seem to figure out how to solve until one day Euler said, I think I know the answer. It's pi squared over 6, which is delightful and surprising, and there's a lot of very fun reasons why that comes about. But for our purposes, we don't really care about the connection to the circle or the interesting discussions that you could have around the sum. It's just that this is an example of a value of this sum. It converges in this particular case. And if you plug in some other exponents into that instead of 2, you can get things that converge faster or things that converge slower. It's a fun exercise just in calculus to ask what's the condition for whether it converges or not. And all around, it makes sense when you have s bigger than 1 that this thing would mean something because you have a bunch of terms that are getting smaller. But if the casual reader were to be very inspired by something like the lore surrounding the Riemann hypothesis, and they find themselves on the Wikipedia page or they're poking around, one of the things they might find is that sometimes into this function, negative values are plugged in. And if they go back and they reference the definition, they're like, hang on, okay, what would that mean? I see the zeta of -1 is -1/12, but that doesn't make sense because it's got 1 plus 2 plus 3 plus 4 and something that gets bigger and bigger. And then they go and they make videos about the sum of the natural numbers equaling -1/12, and everyone gets mad at them, and there's a whole kerfuffle. And you want to sit back and say, okay, what is the actual statement being made here? And for that, you can't have the discussion unless before you get to negative values, you talk a little bit about positive value. Complex values. I suppose you can, but the usual path is going through complex analysis. So we'll think of it as a mapping. For every input, I'm going to draw the inputs with a little yellow dot here, and then the output of the function I'm drawing with a little green dot here. So the input 2 goes to the output pi squared over 6. And the question is, if we extend our notion of, hey, what are all the possible inputs, and instead we ask, what would happen if I plugged in complex values? So maybe I plug in something like 2 plus I, then what does that mean? Now, this is the kind of thing that, assuming you have like a high school level of algebra, it looks a little intimidating at first, but it's not too much to parse and go through step by step and say we can, again, with the aid of visuals, really understand what's being said here. Because if you take 1/2 to the power 2 plus I, that's something that, assuming power rules work the same way with complex numbers as they as you've learned they do with real numbers, you understand half of it. You understand the 1/2 to the power 2 part. And the only other thing to really explain is what it means to raise something to an imaginary power. And this is something that at this point on the channel I had like freshly made a video on, so it had a nice lead in for any people who are regular viewers, where the upshot, of course, is if you parameterize that exponent and you say, okay, maybe instead of plugging in I imagine plugging in all other possible imaginary numbers, the output that I get sits somewhere on a unit circle. And as I kind of move around that input up and down on the imaginary line, the output kind of wanders around that circle, rotating. And it does so with a constant rate if you're moving the yellow dot at constant rate. And the only thing to think about for the sake of the sum that we're going to do is the fact that if it wasn't 1/2 that sits at the base there, but instead you had something like 1/9, you're playing the same game. You're mapping the imaginary line onto the circle, but it moves a little bit faster. So for a particular imaginary number that you plug in, it will have rotated a little bit more. And this gives such a satisfying way to think about the sum that we started with, where let's say initially you picture a nice real number input like our friend 1/2 or 1 plus a 4th plus a 9th, on, and you think of each of those terms as a little vector or just a little line with a relevant length. Then when you add some kind of imaginary part to that input, the lengths don't change. Those all stay the same, so they're kind of like rigid lines, but each one of them rotates a little bit differently. And for each successive term, they rotate a little bit more, so what you end up with is a spiral. And because the first one that you started with, where all those lines were kind of stretched out as far as they could be, if that converged, then certainly as you're spiraling it like this, you would expect it to also converge. So there's going to be some value, some complex number on the plane that is this output. And here I got to just have a little bit too much fun after I had properly written the program and say, okay, if we just grab that yellow dot corresponding to our input and we move it around the plane and say, for various other inputs, what does the spiral sum look like? You can just see what the corresponding output would be. And most importantly, you can be reassured that it'll have some kind of meaningful output as long as the original sum converged, which in our case basically means as long as the real part of what you're starting with was bigger than 1. And so if we're thinking about what is this function, unambiguous, very happy, there's nice convergence and it makes sense when the real part is bigger than 1. For the other part, it doesn't make as much sense yet. But on the way to getting there, visualization can help just a little bit to nudge our minds into something we might want to think about, where what I'm going to do is say, what if we take not just one of the values that I could input in the right half of the plane, what if we take all of them? I'm going to take every single one of them, and then I'm going to pump them through a program that's going to spit out the corresponding output, and I'm going to animate the movement between input and output. And I won't do it for literally everyone, because that'll be dense and filling the plane, but I'll put these grid lines up and then animate each point on those grid lines to kind of represent what's going to happen to everything. And this is one of those things where I had studied this, I had learned about the zeta function, I had thought about it. I didn't really know what was going to happen. I didn't really know what this would look like afterwards. One of the things that, go forward, is helpful to do is add a little bit more density around the input 1. And those of you in the know might think about why you have to add some density around that particular point. And what comes out is basically the whole reason that I decided to make the video. I hadn't necessarily been thinking of covering the Riemann zeta function or talking about analytic continuation or anything like that. But once you see this and you actually map all of the inputs, the whole diagram is just sort of screaming at you how strange it is that there's an abrupt stop, right? You can look at this and you can say, okay, there seems to be this line where everything stops. And one of the very fun things about this is there's all sorts of questions that I think someone could ask if they're watching this that go way beyond anything that the video talks about, that can keep the interest even if it's an expert who feels very well familiar with this concept. For example, you could ask, where is that line? Eyeballing it, you might guess that it's around 0.5. The actual answer is it's around Euler's constant, so it's a little above 0.5. You can ask, why is that the case? Why does it look like a straight line at all? Is it actually a straight line? Now, I don't need to ask those questions, but the point I want to make is just that in trying to visualize it, motivated by making it clearer for the broader public or clearer for a new student, I think the act of doing that also raises the ceiling. Done right, it actually makes it more interesting to someone who feels already familiar with the concept. So the way that the lesson proceeds from here is to essentially point out that because there's this abrupt stop, this whole function seems like it's asking to be continued in some way. That maybe, it's defined well using this sum for some of the complex numbers, but we might have a conditional definition that says beyond those it equals something else. And the question is, what should that something else be? And so if we imagined kind of filling in the rest of the grid, I can preview what that something else ends up looking like, and it does have a kind of local symmetry, I should say. One thing that's potentially misleading about the image is that it insinuates a kind of symmetry entirely left and right on this. But later on in the video, I draw out more extensions of the lines to show that's not quite the case. And this lends itself to just talking about something which is very peculiar to complex functions, that if a student hadn't been studying it would be a fun, novel fact, which is that in a certain sense, even though it feels like you should have a lot of degrees of freedom for what that continuation would be, you just kind of draw the function to do whatever you want it to do for all of those other inputs. While that is true if all you care about is defining some kind of function, or if all you care about is constraining it by being continuous, say, what's surprising and the fun fact to talk about, and can be kind of an upshot of the video that hopefully has a little bit of staying power, is that if you want the constraint that your function has a derivative everywhere, that actually, if there's an extension at all, locks you into only one choice. Which is, of course, one of the fundamental intuitions under complex analysis is how rigid the functions feel in contrast to real functions. And from there, again, it's like if the constraint placed on describing math is to try to visualize everything that's being said, this sentence kind of doesn't cut it. If I really want it to go far, you don't just say derivative. We have to visualize what a derivative means in this context. And so the remainder of the video essentially does that, talks about notions of conformal mappings and what the intuition is for how you would think about whether something is derivative or not, and the fact that completing this diagram is a sort of infinite continuous jigsaw puzzle where every pair of lines that started off at a certain angle, you want them to continue to have that angle and the like. And all of this is just to mention one of the things that I like to keep in mind in the checklist, which is maybe a little peculiar to my case because I've kind of gone hard on this end of try to visualize every single thing, but which I think, taken a little bit more softly, can be mapped to math exposition a little bit more broadly, which is to just ask, are the core ideas given diagrams? It sounds simple, but I think it can go so far. There's another example that comes to mind where a friend of mine named Michael Nielsen, when he was a grad student, wrote what then became like one of the Bibles of quantum computing as far as textbooks are concerned. And he wrote it with a collaborator, Isaiah Chuang, and I was asking him what the collaboration process was like with that. And Nielsen is a very textual learner and thinker, and he would say he would just kind of go and just write out a whole bunch of text and descriptions, essentially procrastinating from his thesis, is the way that he wrote this textbook, which is absurd if you know the textbook at all. And then he would send them along to his collaborator, Chuang, who would then point out, oh, this needs a diagram, this needs a diagram, and basically point out and then often fill out the points that needed some kind of illustration. And the medley was something very beautiful. And I think that having a two-person team like that enabled them to have this forcing function where maybe Michael would have been a little bit less willing to write certain sections if he had also been thinking about the effort that was going to be required to illustrate every single one of them. But with the mind free from having to think about that for himself and someone else taking care of that, it felt like less of a chore maybe. But again, I do kind of want to emphasize that even though it takes time to put together visuals, it doesn't have to. I think just a pencil sketch or something simple in whatever illustration software is your favorite, that it doesn't have to be precise. It can be a simple sketch can go a long way. These don't have to be something that's purely for the student. I think that selfishly on the part of whoever's writing, say writing the textbook or putting together a lecture or putting together a video, sometimes the visuals that you make actually elicit new intuitions. And the act of doing so, at least in my case, many, many times has deepened my own understanding of something. And I feel fairly comfortable projecting that for others, it stands to do the same. This might be particular to programmatic animations more so than a lot of other things, but I think almost everyone's familiar with the fact that when you're just trying to think of something while lying on the couch, somehow it's dramatically less clear than when you go to a whiteboard or you actually pull out your notes and try to sketch something related to it. And letting it be something that's not just a nice to have, but instead sits inside a checklist of what does it mean for my piece to even be done, I think can help force that to come about a little bit more. Now, the next thing that I like to think about, and this is one where, by the way, every single time I do a first draft of something, I violate the principle that I'm about to describe, and then I have to go and realize, oh, wait, no, I should apply this principle. There's something bizarrely unnatural about it, but I really do think it helps to make things clearer. To illustrate it, I'm going to talk about a much simpler piece of math, and instead of doing zeta function type stuff, we're going to go to simple algebra, and I mean like normal high school, middle school algebra, not abstract. And I want you to kind of put yourself back in the state of mind whenever it is the case that you were first learning just basic algebra, whatever age you were, whatever class you might have been in. And I'm going to paint two potential classes, and I want you to just think about how much does each of those classes resonate with this imagined past version of yourself that's sitting there learning it for the first time. So the way that class A proceeds is like this. The teacher starts by asking all of the students, can anyone factor the number 35 for me? And actually, I'll do this. Why not? Anyone in the audience, do you want to shout out the factors of 35? 5 and 7. Excellent. Now, the teacher then asks the students, can anyone please factor the number 143 for me? So, because this is a room full of mathematicians, everyone immediately shouts 11 times 13, which is fun. But the students, maybe they think about it a little bit more. They check whether various numbers go into it. And the one that does their little long division with the 11, they raise their hand with a little bit more time than this crowd would and says 11 times 13. So then the teacher asks, can anyone factor 3,599? Now this is a fun room to do it in. So 59 times 61, great. Fun story, yeah. This does not happen in middle schools. Although I was recently doing something where I brought up this example in a room full of high schoolers, and there was one student who said it. He said the answer. He said it's 59 times 61. And there was an audible gasp from the whole room, because it's absurd if you think about it factoring the normal way. But the teacher says, there's a reason that I led into it the way that I did. And the teacher invites the students to think about how 35 is very close to a square number. It's so close to something round. It's close to 6 times 6. And it maybe doesn't feel like a coincidence that the two factors are also close to 6. It looks kind of like 6 times 6, but you just nudged one up, you nudged one down. Similarly, 143, it's very close. It's just one less than a square number, namely 12 times 12. And it's not a coincidence that the factors, if you kind of squint your eyes, also look like 12 times 12. So if you're just pattern matching, then you might guess that the factor should look something like 60 times something like 60, and if it followed the same exact pattern, it would be one more and one less. And if the teacher wants, they can go through a couple other examples like this, start to convince the class that maybe, just maybe, this kind of wild fact is true. And it lets you look like that person who can receive an audible gasp from all of your classmates for being able to factor a number, which is very fun. And then the teacher can draw out a diagram to help explain what's going on, where if you imagine, what does a square number mean, like 6 squared in this case, you might imagine 6 by 6 boxes. And if we subtract one, you're kind of kicking one off of the corner. And if you rearrange this a little bit, what it means to try to factor the number is to try to arrange all of your boxes into some kind of rectangle. And in this case, we can do that where one of the rectangles has a width that's just one bigger, or the rectangle has a width that's one bigger and then a height that's one smaller. And you can actually generalize this. If instead of kicking off a corner that was just a little 1 by 1 square, if you kicked off a y by y square, you can basically play the same game to factor it to look like x plus y times x minus y. And it's very fun. Again, this gives you a lot of fun mental math tricks, where you can say things that make you seem like a genius, where someone can say, factor the number 9,991, and you can do it without a calculator. Or on the flip side, it's a nice trick for multiplying certain numbers, assuming that you know the square of what sits halfway in between them. So that's class A. Class B starts off by saying, hello class. Today we're going to be studying the difference of squares formula. The difference of squares formula states that if we take x squared minus y squared, this can be factored into x plus y multiplied by x minus y. The formula is very easy. It's not too hard to show, because if we expand out the right-hand side, you see that you have x squared. We subtract off yx, we add y times x, so those two cancel out, and we get y squared. The instruction really doesn't take long. You can give an example, like if you plug in 1, it gives a nice fact that you can factor something into x plus 1 and x minus 1. And then there's a worksheet that you can kind of work through, this is just a worksheet that I found when I was looking for classes on difference of squares formula. Now, Okay, maybe I'm being a little bit unfair and not giving enough personality to the second lesson as I could have. But broadly speaking, if we try to compare what's going on with these two, Class B does something which is so tempting to do in so many other contexts in math, which is that you start with the most powerful thing. You state what the powerful thing is that you're going to do. Usually that takes the form of an abstraction. It's the most true thing. It's kind of easier to show in that case. This is part of what we love about abstraction, is that it's just a lot quicker to verify that that's true than it is to try to come up with some reason why a numerical case where you're gathering around a bunch of squares or stones or whatever you're using to concretize it. And even then, the reasoning doesn't cover all the general cases necessarily, because you'd say, well, does it have to be an integer? Would this work with negative numbers? And would it work with complex numbers? All of that. So that's the temptation of Class B. Class A teaches using data and examples. And it's not that the abstraction isn't a goal. It is the goal. That's the function of the lesson at the end. And it's not that you want to encourage students every single time that they come across the difference of squares formula to picture in their head a little grid of x by x and y, because sometimes you're just in the middle of doing a bunch of other algebra. And the whole point of abstraction is that you don't have to think about that and you can do it more quickly. But I think for the first time that you're seeing it, if you really want it to land inside yourself, it's more helpful to kind of think in terms of layers of abstraction where before getting to the lesson you have in mind, shift yourself one abstraction layer lower. Instead of, in this case, thinking about variables and letters, think about numbers. And then if you show lots of different examples with those numbers, it's kind of like light bulbs in the mind of the student that are thinking of all of those examples. And if there's a certain ineffable character that connects them, the student can kind of think about the things that connect them, the fact that things feel close to squares, or that the two factors that you got are suspiciously close to the square root of the relevant number. And when we did the diagram, in a sense, that's an abstraction layer even lower, where instead of thinking of numbers and numerals representing amounts, you're just looking at the amounts. And you can see the connection between the numerical facts that got you to feel like a wizard and something more direct with those amounts. And by the time you get to the abstraction, it feels so cool and so powerful, because you have a sense for all of the different things underneath that it's touching, all of the different mental math tricks that are encapsulated in such a beautiful and concise formula. It seems a little banal to those of us once you're comfortable with algebra, because it's just one identity out of many. But I think reminding students that every identity that you see in algebra kind of encapsulates this whole body of potential mental math tricks or potential statements about a wide variety of little diagrams you could draw out. There's something about that that feels very inspiring, to me at least. Now Class B, in contrast, it teaches the same topic. It gives you the same ultimate fact. And assuming the students remember the fact, I can't imagine that they would test much more poorly, at least if you do the test with this kind of worksheet that they got their practice on shortly after the lesson. I might question whether they remember the formula as well if you ask them 5 years later or something like that. But if I'm trying to picture what's going on in the kind of depiction of, this isn't literally what's happening in the brain, but my schematic for layers of abstraction in the brain, you're just sort of lighting up the one bulb you care about, and it's not sitting on something else to support it. It hasn't been brought about. There wasn't a sense that it was answering a question or articulating a pattern that already existed in someone's mind. So this is a thing I like to think about as much as I can, where if there's a given topic, I try to draw out what are the relevant layers of abstraction at play here. Now, there's not like a universal hierarchy or something like that, but just as an example for what that might look like, at the bottommost layer, we have things like quantities. One of the very first things we do when we're teaching students math is to get them to go from feeling comfortable with quantities to thinking comfortably with numerals. And eventually everyone gains a certain fluency with this. Maybe there's a couple bumps in the road while they're learning about fractions and doing that, but by and large, everyone kind of gets that layer of abstraction. And then similarly, at some point, instead of talking about numerals, we realize that there's just a lot of facts that are nicer encapsulated with algebra and symbols. And you just communicate more, you can think more quickly with respect to certain things, and it's such a powerful tool. The next layer is, it's not exactly the case that functions abstract the notion of algebra, but kind of it's the case that certain, let's say, facts in calculus that you're learning, you draw out with respect to functions where every instantiation of that function that might come along looks like either algebra or some bit of trigonometry or something there. And so you write out your facts about derivatives and integrals and chain rule and the like, not with respect to specific functions, but instead just in a more abstract setting. And again, the next layer is maybe a little bit silly to think of as like a definitive canonical one, but there's a sense in which functions are a single instance of, or function spaces at least, like a collection of functions, an instance of vector spaces. And a lot of the facts that you might have around functions can fit into a more general framework where things like the derivative and the integral you could think of in terms of linear mappings and the like. And of course, you keep going on and on and on until people get talking to you about higher categories, and it's just a snake that eats its own tail up there. But the point is that whatever layer you're sitting on here, I gave an example in a low set of those layers between numerals and algebra, but I think even at higher layers, I just personally think that it's very helpful for the first time that a student sees something to populate their mind with data of a lower layer before you articulate the higher layer, even if the goal is the higher layer. So if you're teaching linear algebra, for example, even though the whole beauty of linear algebra is the generality, the fact that it's not just describing R2 and R3 and the like, but that there's a whole body of things that you can model with vector spaces and then use facts that you've derived very rigorously just from the axioms to come to conclusions about all the different things that could be vector spaces. Nevertheless, the intuition building phase is probably best done if you populate it with a bunch of examples. Maybe it's good to spread out not just from R2 and R3, but certain other examples of more playful vector spaces that one might come up with. I think one example that comes to mind is just an excellent example to get someone starting to think about more abstract vector spaces is magic squares. And if you teach them the notion of a 3x3 magic square where all of the columns and rows and such have to add up to a certain amount, you then ask someone, how many dimensions is the space of all magic squares? And what's a basis for the magic squares? And that kind of question can get them thinking. Again, it's very concrete. It's a specific instance. It's a very specific kind of vector space. But that starts to invite them to think about what's common across the arrows drawn in 2D space examples that they might have cut their teeth on earlier. So with my checklist, I think what this means is I try to ask, are abstractions preceded with concrete examples? And like I said, for whatever reason, this is one that the first draft, if I write something, just doesn't do it. And I think it's because once you understand something, the way you think about it, or at least the way I think about it, tends to be from the abstraction down. It's frankly a lot easier to think about the difference of squares formula algebraically than it is to try to think about a bunch of mental math tricks or a grid of squares or anything like that. It's just so quick to verify. And then this goes for a lot of other things where the reason we do the abstractions is because it allows for more mental fluency. But then that often can give us a mistake that it means as you're divulging the topic, the thing that is easiest for you, the expert, is necessarily the thing that is most conducive to a new learner coming in. And so by specifically writing it out and letting it be one of the checks, I think it can shift my lessons, hopefully, to be the better. Now, the last one I'd like to talk about is actually something I've only more recently started thinking about, and it's hard to do in videos, and I'm curious about if there's ways to kind of do it better. It's definitely applicable in classrooms. I think done with good writing, it's applicable in textbooks. But one nice thing to illustrate it is a certain study by Manu Kapoor. He even gave a certain TED talk about studies like this. But the one that caught my eye is this paper called Productive Failure in Learning Math. And he focuses on the nature of failure, but to my mind, that's not even the most interesting part. The neat thing here is he has two different classes that he teaches, or that in the experiment are taught to a group of middle school students. And the middle school students are segregated into two different groups. In class A, they experience 2 hours. One is an instruction phase, and following that is a problem-solving phase. And the only difference with the second class, the only difference is that they flipped the order. They did a 1-hour problem-solving phase followed by the instruction phase. And the example matters here because I don't think you can do this for any kind of problem-solving, but it was a well-chosen problem-solving prompt in the case of this class because they were teaching the idea of standard deviation. And the question that they asked was to present the students with 2 different basketball players, and they gave a whole bunch of data over the course of a season of basketball for how many points each one of those players scored. And they were told, Mike and Dave are 2 basketball players, and an award has to be given to the most consistent player of the 2. And the decision has to be made mathematically. And so the students were invited to design as many measures of consistency as they could to determine which of those players is more consistent. It's a very fun exercise, actually. And So the middle schoolers were given 60 minutes to think about this, to look over the data, try to add some things up, use their calculators if they could, come up with some measure of consistency. And a couple of things came out of it. One of them is that the students in that second one that did the problem-solving phase before they did the instruction, they reported that the instruction phase was harder, that they were spending more mental energy on it. Now, the other relevant thing is the number of tactics they came up with. It was a lot higher. There was a lot more variation in the measures of consistency they came up with when they hadn't been taught the proper lesson yet. But the most interesting thing, to me at least, is when they did a post-test on all of this, and they had just questions trying to measure how well the students understood the topic of standard deviation. The questions broke into various different categories. So the ones that were categorized as procedural knowledge, just are you able to carry out the computation and all that, there wasn't really much of a difference between the two camps. But the ones that the researchers marked as measuring conceptual understanding, it was like 2 standard deviations higher in conceptual understanding that the second group had compared to the first. And then questions that were marked as measuring how transferable the knowledge was, were they able to transfer it to a different context? It was like 1 standard deviation higher. And on the one hand, kind of always have to take a little bit of a grain of salt with education studies, and especially if they're small sample sizes and things like that. But to me at least, this one rings very true. The idea that if you seriously engage with a problem before you're told the answer, that actually makes you engage more meaningfully with the answer once it's told to you in the instruction. So I think probably a lot of people in this room have had the experience of toying over some problem, not because it was assigned for homework after a given class was given, but because for whatever reason you just were interested in that problem. And then maybe a little bit later, maybe a couple years later, you come across someone who's answering that problem. They happen to articulate exactly the thing you were looking for. In my experience, that answer sticks so much better than the answers that are given for questions that I hadn't yet been thinking about or toiling over. So the third thing that I put on this checklist is, does the lesson start with some kind of motivating question? Like I said, I think that's kind of hard to do with video because you have to invite the audience to pause and think about it, which some people will do, and that's great. But like realistically, a lot of people are a little bit more passive in that moment. So it seems like something that's much better done in conjunction with instruction, whether that instruction comes in the form of a video or a textbook or something like that. I think a good author with a textbook can kind of do a lot to, at the very least, precede the relevant sections with the right questions, maybe even give some stern, suggestions to the reader that, no, really, stop, think about this. If you really want to engage with it, if you really want to remember it, like, take 5 minutes to close the book and think about this question. But whatever form it takes, I think when the student has actually engaged with something like this, it stands to make the instruction itself land a lot more. And it's not something I've always done, so that's a thing I've been thinking about more and how I can bring that into the future. So I'm curious, actually, what other people would add to this list and what principles they have for a checklist of pedagogy. And just to reiterate the point, I do think that the reason that it's important to have something like this, rather than just letting it be subjective and fuzzy, is because those of us who are mathematically interested, we have a kind of attraction to the definite. And the allure of something that's like exact in the sense that rigor is exact is so tempting that it can sometimes mean we lose sight of the other forms of completion that are just as worthy. And I also want to reiterate, it's not a statement that rigor and clarity necessarily sit in contrast with each other. The best authors definitely achieve both at the same time. It's just when we care about something like clarity with the same verve that we care about something like rigor, with the same sense of satisfaction that comes from looking over a piece and saying, yes, I can officially check this off. That's something that feels like it's achievable when you're looking for a slight cultural shift, whereas fuzzier descriptions like we need to do better just aren't going to apply. So with that, I'd like to thank you all for coming, and thank you.
Thank you, Grant. That was a lot of fun. For those of us like myself who grew up in a time when colored chalk was considered innovative, this was a very refreshing and eye-opening look at the ways that new ideas and technologies can help inform our work. And I think the age of digital textbooks and other kinds of interactive things that combine some of the elements you're talking about are going to offer some very exciting opportunities. We do have a little time for questions. We have a couple of microphones in the aisles, and I would invite you to line up at there or come to those microphones if you'd like to ask a question. I think, Grant, you're up for that, right?
Absolutely, yeah. So, love to answer any questions, and I'll stick around outside of the ballroom afterwards if people want to come say hello. I'm not sure what the protocol here is, but let's say whoever's standing there at the mic first.
Hi. I just wanted to ask you about, in sort of exploring this idea of presenting data first and like this concrete information before getting to abstraction, do you have any thoughts on sort of in that process teaching students that you're not always going to see it, you're not always going to see it the first time, and like getting students comfortable with the idea that math can be hard and this is an exploratory process that isn't necessarily targeted at getting to the abstraction first thing?
Yeah, I think that's such a good point, that even if the back of the mind goal of the expositor is that you've set up this stage so very carefully that surely anyone will follow to the conclusion, setting the expectations with everyone that like epiphany is very rare and discovery is something to be cherished. And if it was something that could happen all the time, it wouldn't be as lovely as it is. I'm not sure of the best ways to do that other than saying it in words and just kind of reassuring now and then, like, hey, it's okay if you don't see this yet. Or maybe holding off from a temptation to use phrases like obviously or like clearly and things of the like. But it's an important point to bring up. I appreciate that.
Thank you.
On the right side here.
Yeah, so there's a phrase that I've heard a couple of times, which is, when teaching math, you should teach the truth, nothing but the truth, but never the whole truth. How do you decide at what point, especially if you're teaching younger students, whatever that means, where it's good to give intuition rather than full rigor, how do you decide at which point to no longer be rigorous?
That's a great question. I think you can always be honest about when you're being hand-wavy, right? Feynman was especially good at this with the Feynman lectures, I know, because like physics is an exercise of constantly lying to people less and less over the course of their education. And he did a good job of like calling out the lies as they took place, saying this is a simplifying assumption. And I don't think it takes that long. And so you can maybe tip your hat to the fact that there might be certain exceptions in certain cases. Or to the extent that's possible, you try to limit the scope of what you're saying such that if there is more complexity outside of it, you're just crystal clear about the setup as you go in. One other brief thought, you said, teach the truth and nothing but the truth. One direction I thought you were going with that was like, when is it fruitful to have little falsehoods through the lesson? I think one form of exposition that is potentially really nice, and a friend of mine gave a name to it, of discovery fiction, is to try to map out a sequence of events that could lead to the discovery of a certain topic. It doesn't have to match the actual history of how something was discovered, but often the shape of it is that you come up with an idea that's just flawed, and then you try to fix it a little bit and fix that flaw, and then that has another flaw, and then you fix it a little bit, and then that has a flaw. And as you proceed like this, sometimes it does a good job motivating why very seemingly arbitrary constructs are put in place to solve a certain problem. And the funny thing about that process is that through most of the lesson, you're describing something that is wrong or something that's not actually useful in the sense that the construct that's sitting in state in that moment isn't ever going to be used. It's just an intermediate step along the way. So I think trying to adhere too much to making sure that at every single step along the way, the objects that you're dealing with really work or the statements are fully true. It's not always helpful to be constrained like that, assuming that you're very honest with the reader or the audience about like where those falsehoods are and why and how they need to be corrected. All right, other question on the left.
Yeah, so suppose you have somebody you want to convey, some kind of cool fact you want to talk about. So I'm sure this is part of your process, but I didn't see it as one of your checks, or as one of your items, so I'm wondering like where this comes in the process. I mean, presumably it has to be early on, but the idea of what is the right way to think about this? I mean, this has to be before planning the whole video, because you have to decide, like, I want to get to here. What is the route? How much time do you spend thinking about what is the right way to think about the final thing. And do you actually have that as one of your checks items that you didn't list?
Yeah, I guess I exist in such a fortuitous situation where I choose the things that I teach, which is not always the case. And so I get to do this really luxurious thing where I just ambiently learn about a lot of stuff. And it only ever bubbles to the point of wanting to make a video about it when it feels like there's that cool thing to show, which is often a slightly different perspective or something that was at least different to me. And so in a lot of ways, it's the 0th law on that list, right? It's the thing that makes it get there. Now, the challenge mode question is, suppose you don't live such a luxurious existence and instead you have an explicit set of things that you're supposed to teach. You know, I don't think there is like the right way to view it necessarily, but what I have found is, like I said, I really like to play around with visualizations of stuff. Sometimes just doing a sort of brain-dead thing to take the important formula and just slowly unpack what each part looks like has been like more fruitful than I would have expected. So one topic that in a certain sense I didn't choose to make, it's just a lot of people were requesting it, was Fourier transforms. I'm like, I don't have anything to say about Fourier transforms. But there was a lot of requests, and I'm like, okay, what can we say here? And honestly, the video I made, it was just, I like look at the definition of it, and I started the innermost part. I'm like, how would you draw this? Okay, how would you draw how these relate? Okay, how would you draw these? Now that we have this drawing, how would you interpret it? How does that drawing change as you tweak this parameter? And kind of literally coding it up along the way, but I don't think you have to. I think it could have just been a whiteboard sketch. And the video ended up really resonating with people, and I think it was just a nice lesson for me that there didn't have to be a priori some great aha that was had, that sometimes just the seemingly brain-dead thing where you go step by step with this strong requirement of having an image in the head for what each part means goes farther than a lot of people might appreciate. Now, it can only be done on the important formulas because it's such a time-consuming process that you wouldn't want for every single thing that comes up in a given lecture to be like, oh, and how do we visualize this? How do we visualize this? You would just never get anywhere, not just in that lecture, but in the whole course. But if you're judicious about which parts deserve that level of deep dive, I actually think it's kind of a fruitful exercise. And whatever topic is maybe sitting in the back of your mind when you ask the question, it's like maybe a fun exercise to sit down and go from the inside out saying, just what would you draw if you had to communicate non-linguistically with someone to convey the idea? Over here.
Hi, Grant. Thanks so much for the talk. It was very enjoyable and enlightening. My question is how you think that this sort of pedagogy checklist is influenced by students' desire to learn. Because fortunately, you know, speaking of luxury, I think it's fair to say that you're in a position where most of the people that you get to teach nowadays are people who are there on purpose and they want to be. But we've all had the experience of having to teach students who really don't want to learn what you're trying to teach them. So how do you think the checklist can maybe be modified in consideration of the fact that a lot of the time in a university setting, or especially in a primary or secondary school setting, there's going to be quite a few students who really are not interested in learning what you want to teach them?
Such a good question. I mean, there's, do any of you listen to the podcast, An Opinionated History of Math, by chance? No? Oh, you'll love it. It's one of my favorite. It's so obscure and like niche, but it's so delightful. But the author of it has on his website this little manifesto about teaching, and he lists out like the axioms of learning. And one of his axioms of learning is essentially your point. Like, people are not, how does he phrase it? He's so much more articulate than I am. But it's essentially, in order for someone to actually learn, they have to want to learn ahead of time. And so you're right, I'm in a luxurious position. Although, you know, it is the case that like every YouTuber thinks about how do you bring someone into the topic if they might not have been thinking about it. And a couple of the standard things for that is like you try to appeal to a thing that interested them before they even walked in the room or before they clicked on the video. A loose example here, I'm not going to claim that things like this will always apply in the classroom, but I think maybe some examples do, and it's worth inviting. I guess last year now, I made this video about Wordle, which was really, on one hand, is jumping on a hype train because nothing was more popular on the internet than Wordle, but it was an excuse to teach information theory. And I can definitively say it reached more people than it would have if I had said, I want to do a lesson about information theory. And I also think to good effect. There was one person who told me that it helped him get a job because there was an interview that he did where a question about Shannon entropy came up and like he had freshly watched the video. He probably would have gotten the job anyway, but I'll take all the credit I can get here. But something like that was, I think, maybe a very special example, but there's probably a lot of different cases where you can find some connection to a thing that maybe isn't in the zeitgeist, but is of a pre-existing interest to the students. And just letting yourself take a little bit of time at the start of a class to let that be a motivating example might go a long way. The other thing, I really do think clarity motivates. Like, on the one hand, yes, it is very helpful to have someone who's already interested in learning, and they sit there and they're willing to absorb whatever you're going to give them, regardless of the clarity. But I also think if you take the time to have something like a compelling diagram to really illustrate what's going on, that is something that doesn't just feed pre-existing interest, but it can generate interest in the first place. And there's a lot of people who've told me that was the thing about the channel that got them sucked in, that they hadn't cared about the channel at all before, but they started watching it because it elucidated something that was a class they were taking or something like that. And so they do feed into each other. But broadly speaking, I think what you bring up is another excellent example of something to sit on the checklist, which is essentially, do you have a compelling reason to believe that the audience sitting in front of you cares to listen to what you're saying? Maybe we do one more? Oh, we better call it? All right. I will happily stand outside the ballroom after to say hello to folks. But thank you, everyone, for coming, and have a great rest of your day.
And as Grant said, he is willing to hang out a little bit, so maybe he can catch some of your other questions. Thank you so much for being here.